Hello again. Tonight we're going to talk about unidentified anomalous phenomena in the form of submersible stuff, how that ties into 2 weeks ago's presentation on advanced forms of propulsion for use in aerospace and space. Like I said, in a prior presentation, we talked about radiation reflection pressure as a means of propulsion for aerospace and in space. But towards the end, we also talked about underwater propulsion because it could be the same source. Since it's moving in water, it'll be at a much reduced speed. This is where it all ties together in space, aerospace, and aquaspace or undersea space. If we could dramatically improve the speed underwater, that would put it on par with the other forms of propulsion. But we need some way of disrupting what is known as the surface tension of the surrounding water. If you've ever watched anyone doing a high dive into a Olympic grade swimming pool, there's always air bubbling up, foaming, frothing the water. This is to break the surface tension of the water so that instead of them from 10 meters up hitting the water like as if it's a brick, they hit the water like as if it's a foam and they don't hurt themselves. Well, we don't need to create a foam. We just need to reduce the surface tension of the water so that when something wants to move through the water, it can move more easily. There are all sorts of boats and ships that do unusual things like hydrofoils, get the bottom of the boat up out of the water so that it's not slowed down by the surface tension of the water. If we could break the surface tension, it might be possible to get to higher speeds than propeller driven things. Maybe not quite to deep space speeds, but maybe aerospace speeds. Maybe not supersonic, because the ripple of the water has a tendency to rip things apart when there's that much energy involved. But the idea is to get moving through the water without having to use something called magnetohydrodynamic propulsion. And if you don't know what that is, watch the movie Hunt for Red October, because that's what it's all about. That requires superconductivity, enormous magnetic fields, and like a nuclear power source. We don't want to have to go to all that. And if you notice the little thing at the bottom, that's the UAP. We need to improve some things first. We need to disrupt the surface tension in the direction that we're traveling. We don't care about it elsewhere, just in the direction we want to go. We want to do so without any moving parts. We want to do so without any like rudders or elevators or vanes. We don't want to have that whole superconductivity thing, but we'd like to make it do what the UAPs do underwater, which is relatively silent. If they're electronic, it could be that if you're really up close to it, you might hear some like fizzing from what's going on to reduce the surface tension, but that noise will be rapidly absorbed into the surrounding water. Much like UAPs, it shouldn't leave any trail. There's no evidence of where it's been. So no bubbles, unlike cavitation, which is where you put bubbles around the outside of your vehicle, which breaks the surface tension, which allows you to move faster. This is why torpedoes are faster than ships. And there's no byproduct chemicals. Like if you're moving a diesel boat through the water, the diesel is going to have chemicals, lubricants, all kinds of things that you can trace through the chemical changes in the water to find the sub. Once they're nuclear, it's a lot harder to do. But in this case, when we break apart the water molecules to reduce the surface tension, there are things called hydroxyl radicals that will be surrounding the vehicle and then will disperse into the adjacent water. So it's not like it's leaving chemicals behind. There is something already in contemporary physics and chemistry that allows you to split water molecules by a catalytic reaction. It's called photocatalytic reaction. Think of it like photosynthesis in plants, but just not involving plants, involving chemistry. So for all the details, here's what a photocatalytic reaction is. Photo meaning involves photons. We produce them by an LED. They don't need to be as short wavelength as ultraviolet or X-ray. They can just be, relatively deep blue. Catalytic, as in it's chemical, but it doesn't consume the chemical. It causes a catalytic reaction, which means you're doing something using the photons that, when mixed with this particular chemical, will basically rip apart the water molecules, breaking up their surface tension. So when you shine the material with this specific wavelength of light in the presence of this material, and then you apply water to the material, it will break apart 2 mole of water, 2 H2O, and it'll decompose it into its molecular components of 2 mole hydrogen, which is 2 H2, and 1 mole oxygen, 1 O2. Not something I'm making up. That's actually something that You can go read science on it. There's a link at the end. If you were to do this in water, it would definitely break up the surface tension of that water. It's not going to vaporize, huge quantities of water, but if you're doing it on the surface of your underwater vessel, the thing that's holding you back, the resistance of the water to your vehicle moving faster, it'll break that surface tension, but you won't be having bubbles coming out of it because the resultant molecules, the hydrogen, oxygen, hydroxyl, will dissolve rapidly back into the surrounding water because there's a lot more of that than there is of the byproducts. As you're moving through it, in the interim, the surface tension surrounding the vehicle will be, as the saying goes, mitigated. That doesn't mean it goes to zero. That just means it's going to be reduced by some meaningful amount. This will allow something solid like your vehicle to move through the water, less deterred by water surface tension. The top speed of your vehicle will be not determined by some rotating propeller, but by how efficient your photocatalytic process is and how much of your vehicle you've got covered that can produce this reaction. So there's another thing called electrolysis, which is used to break apart water molecules. This, however, requires you stick two pieces of metal into the water, and the water has to be doped with certain chemical salts in order to make it ionize and split apart the water, with electricity being dumped in on the two electrodes. This particular process, the photocatalytic process, doesn't require you to put electrodes in the water and doesn't require salts in the water, and there's no chlorine or chemical byproducts that get emitted into the surrounding water that you can trace. You coat the entire surface of the vehicle with this compound, and then you produce the light on the inside and shine it out on it. It's not chemically reactive, but ocean salt water is, so you might want to mildly dope the material with something like platinum. Not cheap, but will make it last longer. And you might want to use some of the fancy means of depositing coatings on materials nowadays we call metamaterials, like the dielectric coating of mirrors used by telescopes, thin film sputtering, to put the material on the outside of your craft. And then you would shine light from the inside into the material on the outside, which would break apart the water molecules on the outside, allowing you to move faster through the water. But it requires photons of a certain energy level in order to have enough energy to work the magic with the catalyst to make it break apart the water molecules. The particular minimum is 1.2 to 2.4 electron volts per photon. And if you want to know what that is compared to things, 1.2 is somewhere in the infrared range, and 2.4 is somewhere in the green range. What we used for the radiation reflection pressure was royal blue, which is 460 nanometers. That's about 2.7 electron volts per photon, more than sufficient. And then you have a short list of really good catalysts to work from, that when you shine this high energy light on them, they'll break apart any water molecules that come into contact with them. Fancy stuff like Tantalum Pentoxide. It's inorganic. It's very good at doing this, but it's rarer due to the tantalum, and it costs more money because it's rare. There's one that's a little less expensive, but has some drawbacks. It requires what they call dopants. It requires not just the bismuth, vanadium, and oxygen, but it also requires some wolfram, W, and molybdenum, which are, the molybdenum is a rare earth metal, so it makes it expensive. But then there's less expensive stuff like titanium dioxide. That's the stuff you see in white paint for pigments and the stuff used in thin film coatings for mirrors. And then the really cheapest stuff, not great at it, but okay, is zinc oxide. The stuff they use to like put on your nose so that the sun doesn't burn your nose. But it tends to oxidize quickly in the presence of energy, so it doesn't last a long time. All of these split water molecules, they're all what is known as hydrophobic. They don't mix well with water itself unless you put the energy into them. And they're water insoluble, which means the material itself doesn't dissolve in just regular water, although zinc oxide is kind of giving up things in salt water. Now, most of these materials will appear light in color, like zinc oxide is bright white and quite reflective, kind of like those Tic Tacs you see. Most of the time when you do chemistry, things are exothermic, which means they make heat. So you do chemistry and you get heat as a waste product because it's not 100% efficient. But in this particular case, the chemistry is what is known as endothermic, which means it cools things down. When you produce the light to go to the material and it splits apart the water molecules, it actually needs more energy. So it draws the energy down from the chemistry of the water, making the materials that it splits from the water cooler, lower temperature, lower energy. The water temperature in immediate proximity to the vehicle would be cooler, be reduced. It's not going to freeze, but it's cooler. Now, as water depth increases, the temperature decreases. So if you go down deeper, you're not going to notice it as much because the infrared signature, your ability to detect this particular vehicle submerged, like a UAP, as the saying goes, make a hole in the water. Because if you're looking for something to be hot, this will be cooler, and it's a lot harder to detect something that's a little bit cooler than something that's a lot hotter. The faster it goes, the darker the infrared hole will be. If it stops, it will start taking on the temperature of the surrounding water. So it'll disappear in infrared because it'll be the same as everything else around it. Now, if it was exothermic, you could spot the IR. It would stay hot longer in the water, making it easily detectable. But since it's endothermic, it gets cooler. It's going to take a while for you to notice that it's cooler just there, not everywhere. The other thing is this particular catalytic separation of water molecules, it doesn't rely upon chemistry in the water. It's just looking for the water molecules themselves. It's kind of doesn't care so much about the temperature of the water or the actual water pressure, the pressure of the water, how deep can you go? But since it doesn't need salts in the water, it'll work in both fresh water and salt water. If the temperature of the surrounding water were a little bit warmer, it might negatively affect the process a little bit. As you go deeper, the temperature is reduced, so efficiency improves with depth. As you go deeper, so the water pressure increases. As long as there's sufficient disruption of the water's surface tension around you, the pressure won't really make a difference. It might slow you down a little bit because you're having to expend more, but you might still be faster than something that has propellers at the same depth. If you've ever studied oceanography and submarines moving under the sea, you might hear the term thermoclines. That's where you have water towards the top, towards the surface that is of a general certain temperature. And then you have kind of a barrier where the temperature is different. And then you have the colder stuff down towards the bottom. If it's salt water, the density of the water changes with the temperature. So you start up here and your ship can easily move through that water. And then you go through the thermocline and it's kind of like punching through something much thicker to get to the saltier water beneath it. The speed of submergence and your buoyancy is something you need to control to get through the thermoclines. But in this particular case, there is no ballast tank. There is no issue with buoyancy. You just disrupt the water molecules on the bottom of your vehicle and you descend. And if you leave the electronics turned on, you can stay down there. You don't have to counteract the buoyancy of the ballast tank. So how low could you go? We're not relating temperature or salinity or buoyancy because we have something that disrupts the water surface tension. You have to optimize whatever you're doing in this process to give you enough oomph to go lower and lower. The maximum depth is dependent upon how good the process is, how efficient the materials are, how thick the coverage, nanoscale, probably better. But you're trying to produce as much disruption in the water as you can. But you need to pay attention to crush depth because if you have any sort of failure, if you're below the durability of whatever your capsule is, you're probably going to implode quickly. Not good if you have people on board. So I'd say keep it to about 8 meters, 26 feet, kind of snorkel limit. And that would be deep enough that unless the water's like Bahamas clear or Fiji clear, you're going to be deep enough that you won't be easily spotted. If you're talking about an ocean or a lake or a river, you get 30 feet down and it's really dark quickly. Now, if you have a big enough tic-tac shape, even if you're 30 feet under the water, you're going to make a bulge in the water as you go zooming along underwater. There'll be a bump on the surface of the water. So that might give you away. You're still underwater, operating at a speed faster than boat propellers could move boats. So you can outpace things. But if you really want to, like, oh, they're after me, they know where I'm at, I need to get away, ascend, go from underwater to aerospace, and then quickly elevate up to the edge of the atmosphere. Obviously, they're not going to chase you there. And there's some military observational evidence that that's how they get away from military. Here's something that may not be thought of initially is that if you're making, let's say, in the direction of travel of your vehicle, the surface tension to be reduced, that means you have less pressure on the front. And since you're not doing anything on the back, you have more pressure on the back. So it's going to be pushing for you to go forward. Think of it like if you've ever drank boba tea, where they have the little tapioca spheres inside there. When you reduce the pressure in the straw, even though the boba is beneath the surface of the tea down in the bottom, it still comes up. And same sort of thing. Think of it as it's countering surface tension on one side and leaving the surface tension normally on the other side, so it's pushing it. If you're into like Star Trek analogies, think of it like an underwater warp bubble. Here's another thing to think about, which is when you're traveling through air, when you're traveling in the Earth's atmosphere, and you want to go supersonic. Why is it so hard to go supersonic? Well, there's air pressure. Well, it could be that, yeah, the air is part of it, but think of it as if you're underwater and you can't go fast because the water offers resistance to movement, and then you disrupt that resistance to movement, the surface tension, and now you can go faster. Wouldn't the same thing hold true if the density was lower but still existed? Like air has water vapor in it, and if you don't disrupt the water vapor, if you don't disrupt the molecules of water in the air, then your supersonic aircraft has to push against that and move them out of the way. If you had the same technology for photocatalytic process, then you could do the same thing in air that you do underwater. As altitude increases, temperature decreases, and the reduction in temperature actually increases the relative humidity. If you say, I've got nearly a vacuum up here, I've got equipment in my house where I could draw down a vacuum, just getting it to low air pressure is not enough. You have to remove the water vapor as well to get that last amount of vacuum that you need. Maybe sonic booms from supersonic aircraft is nothing more than the water vapor conducting the transfer of energy in the presence of the aircraft. If you could disrupt the surface tension of the water vapor in air, maybe you could go supersonic without having a sonic boom, which is one of the characteristics of a UAP. If the photons that are coming out of our propulsion system were passed over this catalytic converter, since they're in the right wavelength, they should also dispel the surface tension of the water that's in the water vapor of the atmosphere. Might explain why UAPs travel supersonic but don't have a sonic boom. The final UAP behaviors were, okay, we've done all the air stuff and space stuff, and what about the underwater stuff? Well, now you have the underwater stuff and how to make it go faster underwater with no cavitation, no hydrodynamic surfaces, no vanes and rudders and stuff, not affected by water pressure or thermoclines, temperatures, faster than propeller-driven things without having moving parts, potentially as fast as aircraft, but underwater, although maybe not supersonic. And the same capability might be useful in mitigating sonic booms once you're above the water. This would give you all the remaining abilities you would need to demonstrate what UAPs do without requiring the mandates of magnetohydrodynamic propulsion, the superconducting, the big magnets, the nuclear reactor for the power. But somebody would say, prove it, demonstrate it. Well, here's what I tried to do. I bought a couple of glass vials. These are medical sample tubes. I 3D printed a Tic Tac, a little Tic Tac. I printed it in black, and then I coated it with zinc oxide. The glue I used was probably a bad choice, but I coated it in zinc oxide. I filled the inside of it with material that makes it not quite as buoyant, but I made a problem there. I'll just explain that on the next slide. But the idea would be, if I can get this thing with the zinc coating on the outside, then I can put that inside of a water-filled tube, and if I shine the right energy LED through the glass, if it's the right kind of glass, borosilicate glass, that the near UV light will go through it, then I should be able to make this Tic Tac move towards the light because it's disrupting the water tension on that side and not the other side, and you get the Bobo straw effect. That's what I worked on, and here's what I got. And it didn't move, and I found out why it didn't move. As the adhesive that I sprayed onto the outside of my Tic Tac dried, it became gloppy, gloopy. It became lumpy. It did not permit the zinc oxide to make a nice, dirty, dusty uniform coating on the outside of it. You can see it in the pictures down below. It's kind of lumpy. And then I pushed it in, filled it up with water, and put more water in, so it was like right up to the edge. And then I popped the cork in and squeezed out any excess water. When I was trying to seal, because I had a little nozzle in that I could use a hypodermic to inject material into the capsule to fill it up. When I went to seal it, I said, maybe I'll use a little bit of heat to heat up the capsule to make it squeeze out like any excess. And I went too far with the heat. It didn't melt the capsule, but what it did do is it heated it up so that it bubbled out any of the excess thick glue that I put inside there to reduce the buoyancy. And when it did that, it reduced the air inside the capsule. And I don't know if you know this or not, but if you take a balloon and you inject some air into it and you take it underwater and you let go of it, it's going to rise to the surface. If instead of it being a soft vinyl balloon, it's a hard shell and you take the air out of it, it goes to the surface even faster. So what I did by heating it was actually make it more buoyant rather than less buoyant. But when I laid the capsule on its side flat, it rose to the glass in the vial, basically making some pressure against the inside of the glass. Not enormous, just enough. But since the adhesive was on the outside and the adhesive was being saturated in water, it caused the capsule to adhere, not permanently, but stick to the inside of the vial. And if I sort of tilted it back and forth, the capsule would move inside of it. But if I just let it sit there, it kind of like stuck to the inside of the glass. The effect that I was producing was not sufficient to break that adhesion/buoyant contact with the vial. The test needs to be performed with these things mitigated, maybe by somebody else who'll watch this video. But it was interesting to see that the royal blue LED made the zinc oxide fluoresce light green. And I used a very bright white light on it, thinking that would give it more power. It just was very reflective. Now, if you look to the right-hand end of the capsule, you'll see a little air bubble. That was air that was trapped on the outside of the capsule. Remember, I squeezed all the air out from the top. So that's not, I didn't fill it up with enough water. That's air that was trapped in all the nooks and crannies on the outside of that not smooth surface and made a little air bubble. And all the air got together and was at that end. It was actually laying sideways. So this was interesting. Yep, it's maybe just not optimal, but there was an effect. I upped the energy level and the flux, the number of photons per second, to use my deep blue 2-watt laser pointer, open the lens up where it would cover the entire front of the capsule. And nope, it still didn't move the capsule. That buoyancy adhesion was too great, couldn't break it. But what it did do was it increased the size of that air bubble because the zinc oxide, under the presence of the brighter blue light, was actually breaking apart the water molecules. The catalytic effect was proven, but I didn't have anything optimal enough to make enough of effect. And I used the wrong kind of adhesive, and it didn't make a nice, smooth, thin, uniform coating, but it was still tacky enough that it mixed with the water in it. It caused it to stick to the inside of the glass. So if we were building a UAP kind of thing, then now that we know that these particular materials are crystalline in nature, they can be mixed with other crystalline materials, glasses, and you can actually make kind of a porcelain covering for the outside of your vehicle that you could shine the appropriate energy light from the inside to the outside. That might make it more efficient to produce the vehicle. It might mean you get more photons engaging with more crystals of the material. It might make the process more uniform over the vehicle, and it might make it go faster underwater. But as I was looking at this from a clandestine projects perspective, if in the previous presentation, we were talking about royal blue or 460 nanometer LEDs as maybe that's something that they had to make in technology and physics because they needed them for, I don't know, Blu-ray players or RGB LEDs for TVs. It turns out, no, it's a particular wavelength, 460 nanometers, that they needed to produce more light, more flux, more photons per second, and cheaper to mass manufacture. Well, maybe it was for Blu-ray players, but Blu-ray uses 405 nanometer diode lasers, not 460. And RGB TVs, the B in blue, needs 440 to 470, not a narrow wavelength, but a broad wavelength to get all of those different shades of blues. So the technology that produces 460 nanometer cheap royal blue LEDs had nothing to do with Blu-ray players or RGB TV. Turns out if you look at the history of blue LEDs, it was done in Japan, and some people question the amount of money being spent to achieve mass production of bright blue LEDs, particular wavelength. Turns out after spending a lot of money, some of it questioned. 2014, the Nobel in Physics was awarded to a team in Japan for creating these bright blue, mass-produced, low-cost LEDs. The lead guy that did that, Mr. Nakamura, he moved from Japan. He now works for University of California, Santa Barbara in the U.S. If you know the colleges in California, they have a good tie into the military-industrial complex. Maybe the annoying bright blue power LEDs on all your home electronics is as a result of the dirt cheap blue LEDs, but that's just a byproduct. It may be that they really needed the 460 nanometer LEDs for UAP vehicles. Just a thought. Y'all have a nice day now. So in summary, we talked about radiation reflection pressure and how we could use this photocatalytic process in conjunction with it. And now we have all the recognized UAP behaviors, and we can produce vehicles that don't need aerodynamic surfaces, don't need hydrodynamic surfaces. They're photonic. They do physics conversions. Maybe there are companies that are already doing this. That's where the UAPs are coming from, but don't know. But this would be for sublight, not C, not faster than light, but it would work for space, aerospace, and submersibles. And maybe you need the bigger UAPs to take these sublight UAPs into them because you need a bigger ship for the faster than light drive and its power sources. Everything's up for optimization that I've discussed. The power that you need to generate for producing the photons or controlling the electronics, how many emitters, the LEDs that you need, how good they are, wavelength, the power, the shape of the lens, semiconductor efficiencies. I know we've seen memetics come into that. That's how do you take the effect of a glow bug, a firefly, and apply that to LEDs, and you get a lot more photons out for power in, still advancing semiconductor efficiencies for LEDs. And then for the reflectors, it's if you make a frustum, do you coat the inside with just something that's reflective, or do you dope it with something that will change the index of refraction to make more of the reflection momentum go forward? If you're doing photocatalytics, do you take them as is? Do you create new chemical formulas for them? How thin do you make them? We know that if you make something near like 1 atom thick, you get a lot better end result. And maybe the propulsion and the photocatalytic process can share the same photon wavelength. That would be meaningful. And then you have to develop all the necessary means of detecting how high you are, how fast you're accelerating, what speed you're at, both above the water and below it. So all kinds of new sensors and software to control them. Presuming that there's going to be resources applied to do this. If something has a negative buoyancy in air, it rises faster, like a helium-filled balloon, goes higher. Something has a negative buoyancy in water, that's easy enough to do. You just don't fill it full of water. In the lower atmosphere, we need to be able to have negative buoyancy as well to make the craft lighter. I'll just leave it at that for now. Maybe a future presentation on something called vacuum aircraft. And then links as usual. And then if you want to study the history of blue LEDs, okay, comments, questions?
That's something I haven't thought of.
Well, I mean, that was the thing that was left is, okay, so we did this radiation reflection pressure thing, and that covers all the aerospace and the outer space, but UAPs go underwater. How do you do that? Well, now you know how you do that. But whenever anybody says, how would they do that? I have no idea how they would do that. Well, there you go. Maybe they're already doing it. Maybe it's, we pay for clandestine aircraft to make sure we're always, 20 years ahead. That's, if you remember back in the late 1950s, they were talking about U-2 spy planes because they needed them in the 60s. And then when they were in the 60s and they found out that wasn't good enough, they created the Project Oxcart and SR-71 and things like that to get even better. And now we're like, hypersonic. What do we do next? Outmaneuver, which is what the UAPs do. They outmaneuver.
Yeah.
And then, well, if you're going to shoot something at them, how do they escape it? Go underwater. But we have submarines down there. Submarine doesn't do you much good if you can't spot the enemy and they can go faster than you.
Yeah.
If it can go faster than a cavitating torpedo, then it's like an SR-71 can go faster than your hypersonic missile.
And also the maneuverability, being able to change direction in a hurry.
And it may not be as exotic. It might not be a sharp 90-degree turn, but if they can make a 70-degree turn, that would be far better than some jet on afterburners doing a bank and having like a 20-mile turn radius. If you have a 1-mile turn radius and they've got a 20-mile turn radius, from their perspective, it looks like you turned on a dime, but you didn't. Okay. Any comments or questions before I stop recording? Hearing nothing.